Welcome students, and in this video we are going to talk about the existence and uniqueness theorem. Okay, in other words, this is also maybe called as a fundamental theorem of OD. We do not call it like that, but till you know why I want to put emphasis on fundamental theorem, because this is probably the most important theorem which you can learn in ODs, right? Okay, so first of all, what am I trying to do here? First of all, we start with a system, right? So let us consider this system. Let us consider n cross n system. Clear? N cross n system given by x prime equals to a, right, which depends on we are not looking for a linear system, but we are looking for x prime equals to f of x. That's a system, right? Okay, and see here, f is a given function. Clear? F is a given function, and we are looking at a system x prime equals to f of x, and now we want to see whether can we say something about the existence of solution or not. Okay, so before I say the existence of solution, first of all we need to understand what a solution, what do I mean by a solution. Okay, solution. So let's call this equation of x prime equals to f of x. Yes, okay, what do we mean by a solution, right? So you see, a solution of this system essentially of x prime equals to f of x, okay, and let's say at the initial condition x at the point t naught is x naught. Okay, this is the whole system. So essentially x prime equals to f of x is the rule according to which the particle moves, and initially at the time t equals to t naught, let's say you can take t naught to be 0 also, x equals to t equals to t naught, the position is essentially at x naught, which is in Rn, right? So which is in Rn, x naught is in Rn. So basically we are talking about a n cross n system, right? Okay, so a solution of this system is a differentiable function, continuously differentiable, sorry, let me put it this way, continuously differentiable function. You don't need continuously differentiable, but for all purposes we will be using it, continuous differentiable function. And what is the function? This is a function x from I to Rn. What is I? I is some interval in let's say R, right? I is subset of R. Clear? Okay, so essentially if you have a function I from Rn, x from I to Rn, okay, what does this mean? This means that this is nothing but actually you are looking at a curve such that for all t in I, clear, x prime of t, so basically it has to satisfy for all t, right? So it is capital F of x of t, clear, and moreover x at the point t naught, x should be such that x at the point t naught has to be x naught, clear. So this has to satisfy for all t in I, and at the initial point they should pass through the vector x naught. So essentially what very vaguely speaking, what it means is this. See, x prime equals to, so basically let's say that there is a particle, right, which is moving with time, okay, which is moving with time in some R2 or R3, okay, in some space R2, let's say R2, it is moving in R2, okay, with time it is moving. So at t equals to t naught, let's say, okay, it is somewhere here, so this is t equals to t naught, okay, and what happens is it is actually moving along. Let's just assume for now that it is moving like this here. So as t increases, it goes on doing this. Now you see, what is happening is this: what is x prime equals to f of x is actually the rule, right? See, f is a vector field. F here is a vector field from Rn to Rn. Okay, is a vector field. Now, what x does, what f does is, so n equals to 2 in this case. Okay, what this thing says is the rule. So it will actually dictate how the particle moves. Okay, so at every point it will give you, if you will give a specific direction. Okay, and it will say you have to move in that direction. So this is the rule according to which the particle moves. And the initial condition x at the point t naught equals to x naught means you are basically saying that the particle has to start from this point. Okay, so this is the rule according to which the particle moves, and this is the x at the point t naught equals to x naught will actually tell you that where to start. Okay, so basically the question of finding a solution is this: you have a particle. Yeah, you are basically looking for a particle which starts from, whose position at the point t naught is, let's say, x naught, and such that at any point, okay, at any point t, whatever the domain, so basically t is in AB, right? So any point t in AB, x prime of t, so the the tangent vector at that point, right, t, has to be matching with the value of the vector field at that point. Okay. So I hope this is clear. This is just an intuition. It's not, okay, not very mathematical, but the thing is, I think the idea is clear. Okay, so that is there, right? Now, and you see here I have to write down f is a given vector field, given, not function but vector. I should write it as vector field, given vector field. Okay, given vector field. Now, you see, what happens is this. Let's say that, so let's take some examples and see, examples of existence evidence. So let's come back to existence. So now that the concept of solutions is clear, okay, examples. So what are the examples which you are looking for? So is there a solution or not? First of all, existence and uniqueness says the first thing is existence, of course, as the name suggests, whether you have a solution or not. And secondly, you also need to know that if there is a solution, is it unique? Clear? Okay, so let's look at some examples. See, let's say that, look at this example, y prime equals to 0, just a first order equation. Okay, so first order OD, right? Now you see, you do realize that if I am writing y prime equals to 0, that will imply y of t equals to constant, right? For any constant will what? So essentially the solution, okay, so therefore the solution is a family of curve, right? The solution of such a equation, for solution of such an equation is a family of curve, right? Is a family of curves. Clear? Is a family of curves. Now, so does there exist a solution? Of course. How many solutions are there? They are infinite, because C is varying in R. Now the thing is this. So uniqueness is not here. So generally speaking, if you are not specifying the initial data, right, the uniqueness part won't work. Okay. So basically most of the times maybe there will be a solution, but the thing is you cannot guarantee the uniqueness. Okay. So basically now you see, if I am putting, so additionally, let's say that y at the point 0 is 0. So basically I am specifying that at the point 0, y has to pass through 0, right? Then you see, y identically equals to 0 is the only solution. It's the only solution. Okay? It's the only solution. So you do realize that once I put a specific point, that I'm saying that my curve has to pass through this point, right? So at t equals to 0, it has to pass through 0. So then what happens is the uniqueness is there. Okay. Now the question is this. See, I am saying is the only solution. How do you know this is the only solution? That is another question. Okay. Let's just quickly see what we can say. See, let's say that if so, this is how generally we try to prove this. So if y1 and y2 are two distinct solution, let's say two distinct solution of this equation. Let's say y prime equals to 0, y at the point 0 equals to 0 I wrote, so maybe let's say y naught. Okay, y naught can be 0, doesn't matter, y naught is in R. Okay, so let's see what happens. If there are two distinct solutions, then define, if one defines, it is very trivial, right, y to be y1 minus y2, then that will imply what? That y prime is y1 prime minus y2 prime, okay, which is again 0. Clear? And that will actually imply that y of t is constant. Okay, and since y0 is 0, so that constant has to be y0, right? That constant has to be y0. But you see, the thing is, constant is not y0 here, because y is y1 minus y2, and y at the point, so y1 at the point 0 is y0, and y2 at the point 0 is y0. So y1 minus y2, y1 0 minus y2 0 is 0 essentially. So this is nothing but 0. Okay, 0. Right? So y2 is 0. Yt is 0. Right? Now that will imply that y1t equals to y2 of t. Okay? The question is this. Again, is it clear that if yt equals to 0 is the only solution, there are no other solution? Okay, so from here it is quite clear that that has to be the case, right? There is no other option. So in this case, the thing is, this problem has a unique solution. Okay? So that is more or less done. But the thing is this, for a general problem, finding the uniqueness, even though you have found the existence, finding a uniqueness is a very, very difficult question. Okay, so we need to know how to do that. Okay, so for that we are going to look at some a very, very important thing. But before I do that, let us look at another example. Okay, so the question is this. Let's say that if I am putting an initial value, okay, so please remember this thing, the existence in initial theorem, this holds for, so for initial value problem, initial value, very, very important, initial value problem. I hope you understand what initial value problem means. Initial value problem means that you are essentially looking at one point, so you are specifying that the particle is starting from some point. That's the only data which you have, initial value. Okay, so let's look at another. So basically, let me put it this way: does all initial value problem has a unique solution? Let's just put it this way. So they may not be. So for example, let's say that y prime of t equals to 3 y to the power 2 by 3. Let's look at this equation. Yes, I hope you guys can solve this equation. Of course, you do realize that y0 equals to, and y0 equals to 0. Let's just put this condition. This is the kind of problem. So clearly y identical equals to 0 is always a solution, right? Always a solution. See, if y is identical equals to 0, y prime is 0, and again this part is also 0. So left and right hand side is 0 for all t, and of course y is identically 0, so y at the point 0 has to be 0, right? So that is always there, right? Now you see also y1 of t, let's call another thing, y1 of t equals to t cube also solves the equation. Okay, so you see we have actually, and you can easily check, so please check this part, that yt equals to t cube also satisfies the equation. Okay, right. So, and actually moreover, you can actually show that moreover, for any tau greater than 0, okay, you can show that this family u tau of t, okay, y tau of t, given by 0 if t is less than tau, and t minus tau cube if t is greater than tau. Okay, this problem, so this family also satisfies the equation. So you do realize that, I mean, it doesn't have to be that the initial value problem has to have a unique solution, right? Unique solution. Okay, right. So does it always have to have solution? What do you guys think? Even that is true. Okay, so let's look at, this is B. Now see another example. Let's look at this problem. Let's say consider this problem. Y prime equals to 1 and minus 1. 1 if t is negative, if t is greater than equal 0. That's the equation. Now you have to do it, you guys have to do it yourself. See, first of all, here the source term means the right hand side. So see, remark, we put it as a remark. The right hand side is not continuous. Okay, it's a valid function of course, but it is not continuous in R. Okay, see, if it is not continuous, if it is a solution, then y prime t has to be equals to 1 and minus 1. 1 for t negative and minus 1 for t greater than equal 0. So this is not continuous at 0. Okay, so y prime t, if there is a solution, then that solution, the derivative at the point 0 doesn't have to exist, right? So this sorry, it has to exist, but what I'm trying to say is this, it doesn't have to be continuous. Okay, so that will imply that y as a solution, y is only differentiable. Doesn't have to be continuously differentiable. Of course the derivative exists, but the thing is, the derivative at the point 0 is not continuous. So basically y is only differentiable, not c1. So it is not continuously differentiable, right? So that's the issue here. So not issue, but the thing is, this is the idea of solution. So in this case, the solution is not continuously differentiable function, but just a differentiable function. Now you can check that there does not exist, this is the sign, does not exist any solution. Yes, so you understand what do I mean by solution of this problem? There does not exist any solution. And see, here whenever I'm saying that there does not exist any solution, so solution in this sense, satisfying y at the point 0 is 0. Okay, see, the thing is, what I'm trying to say is this: y at the point 0 is 0. That sort of solution, if you are looking for, there is no such solution which will be satisfied in this case. Clear? That is what I'm trying to say. Okay, so now that part is clear, so essentially what we learned up till now is this. Let's do a quick summary. So essentially we are looking for a initial value problem, right? Initial value problem. Let me put it this way: initial value problem. And what sort of problem are we looking at? We are looking at a first order equation, f prime equals to f of x. So we are looking for a system, and for a special case it becomes like a usual ODE. Okay, so for this equation, what we have seen for this system, essentially what we have seen is this: x at the point t naught is x naught. Okay, there may be no solution. There may be a unique solution, or there may be like infinitely many solution, Okay, so what is the guarantee that if I give you any problem, you can actually say that, let's say that equation has a solution, and if the solution is unique or not. Okay, so that is the theorem which you are going to do. So this is called a fundamental local theorem. So this is, the theorem is local, so this is called a fundamental local theorem. Fundamental local theorem. Why local? Because this is not the theorem which I am going to give you is not a unique like a global theorem. Local theorem of ODE. Okay, let's look at the theorem here. So this is called Picard's theorem, Picard's existence in universe. So consider the initial value problem. And what is the initial value problem? A prime equals to x prime equals to f of x at the point 0 is x naught, clear, which is in Rn. So basically we are looking for an n cross n system. Suppose, and this is the condition which we need, f is okay, f from Rn to Rn, let me put it this way. Suppose f from Rn to Rn is continuously differentiable. Okay, so f is a vector field which is continuously differentiable. So basically what it means is all possible, so basically the first order derivative it exists and that is going to be continuous. Okay, right. So this is the only condition. So you are given this equation, and the condition which I am just asking, this very minimal condition, what I am saying is f has to be just continuously differentiable. If that is the case, then you can guarantee that there exists a unique solution, a very important unique, let's put it in a box, unique, okay, solution. Let me call this is as A1, unique solution to 1, unique solution to the initial value problem 1, to the initial value problem 1, clear? So in a more mathematical context, what does it mean? Let us put it this way. So that is, there exists a positive, some a. This a and this is not same. Let's call it b. Let's say, or whatever. Let's say epsilon. There exists epsilon positive and a unique solution x from minus epsilon to epsilon to Rn, clear? So you see, I am looking for a solution. So I am saying that I am looking for a curve which passes through the origin, right? And at the origin, at t equals to 0, the curve should pass through the vector x naught. That's what I am saying. x0 equals to x naught. That is what it means. It means that at t equals to 0, so when the time is 0, the curve is at the vector x naught, yes, and then the curve is moving, yes, according to the rule x prime equals to f of x. I want to know whether there is such a curve or not. What you can say is in a small neighborhood of t, so basically minus epsilon and plus epsilon, okay, time, in a small time, minus epsilon and plus epsilon, you can actually say that there is such a curve given f is continuously differentiable. So basically a unique solution like this satisfying x0 equals to x0, clear? Okay, so the proof of this thing we have to do, and before we go on, I think this is okay, right? Yeah. Okay, so yes, before we go on, in the first lecture, yes, in the first week we talked about this, right? So but again, let us just quickly recall. I am not going to do the proof. Now we are going to recall some concepts and then we are going to do the proof. Okay. See that let omega subset of Rn be an open set. So I am looking for a open set. A function capital F from omega subset of Rn to Rn, clear? is said to be Lipschitz continuous. Lipschitz continuous. We are going to need this concept here. That is why we are just saying Lipschitz continuous on omega if there exists k. This k of course is positive such that f of y minus f of x. So please understand this, f of x and f of y. F is a Rn to Rn function, right? It's a vector field. So whenever I am saying f of x minus f of y, this element is in Rn, this element is in Rn. So I am taking the difference of two vectors and I am taking the modulus, the norm of that. So this norm, think of it as a norm in Rn. Okay, so that will always be dominated by constant times norm of y minus x. So again y minus x and y are in Rn. So this is also the Rn norm. Okay, this should hold for all xy in xy omega. Okay, right. Now the k, the constant k, this is very important. This k depends only on omega, and not on any particular point. Okay, so k only depends on omega and is called the Lipschitz constant. This we already did. So Lipschitz constant for f, for capital F. Okay, and you can also recall that we call so we say also f is locally Lipschitz. Okay, if each point in omega, okay, has a neighborhood what is the neighborhood? Let's say omega prime, which is subset of omega, okay, such that when you restrict f to omega prime, so when you restrict f to omega prime, it is going to be Lipschitz. Clear? Okay, and you do realize that in this case there is a Lipschitz constant, but that actually is going to vary according to omega prime. Yes, so we have already covered all of this in the first week, so I am not going to elaborate this, but basically this is just to recall. Yes, okay. Now you see why the question is this: why are you suddenly talking about Lipschitz continuity here? Because the statement of the theorem does not say anything about Lipschitz continuity, but we are going to use this. This is a very, very important property in that sense. Okay, so before we do that, again we have to go through a small lemma. So what is the lemma? So it says that let capital F from omega subset of Rn to Rn. So we are looking for a continuously differentiable vector field. So let's say this is continuously differentiable. Then capital F is locally Lipschitz. I should write it properly. It is capital L Lipschitz. Okay. So what it means is, see, it is saying that if you have a continuously differentiable function, see the statement of the theorem which we are working with, it has that if the vector field, okay, is continuously differentiable, C1, that is, this is C1, right? So what we are saying is, if the vector field in question is continuously differentiable, then we can say that the vector field is locally Lipschitz. Okay. So what is the proof? The proof is this. So see, suppose that capital F, okay, from omega to Rn is C1. Let's just say it is C1, and we start with x naught, which is in omega. See, f is C1 given to us, right? And I have to show local ellipsis. So basically, I will start with a point x naught, which is where I will show that there is a neighborhood around x naught where f restricted to that neighborhood is ellipsis. That's what you have to show. Okay. So now let epsilon positive be small enough such that omega epsilon bar, so this closure of omega epsilon, okay, so this I am defining as the closed ball, okay, so this is x minus x naught, so this is the set of all those x, okay, in omega such that x minus x naught, so this is norm, this is Rn, okay, so norm of x minus x naught is less than equals to epsilon. Clear? Okay, so this is I am defining this thing here, and for now I don't want to use that bar all the time, so let's just say this is omega O epsilon, let's just call it O epsilon, that will be better. Okay, now you see O epsilon, what is happening is this, f is C1, right? F is C1 and it is defined in whole omega, right? So you can actually have that the norm of df of x, okay, df of x, okay, this is always dominated by some upper bound, okay. So essentially what I am trying to say is this, see, f is C1, right? That will imply that the derivative of f at some point x is a linear map from Rn to Rn, right, which is again continuous because this is C1, right? So dfx is continuous, See, if f is C1, df that map is continuous map. Again, df at a particular point x is a linear map, that is different, and but anyways here in our case dfx is continuous, right? And you see this O epsilon, this set is compact, okay. So if you are choosing your omega the point x from O epsilon, okay, so this holds for all x in O epsilon, okay. So if you are choosing your x from O epsilons, what is happening is this, that df you are basically looking at you are restricting it to a compact set, and we know that a continuous function on a compact set is going to be bounded. So basically it attains a maximum somewhere on the compact set, so that is why, that is what I wrote. So the norm of dfx is bounded. Clear? Okay. Also you note that since this is closed set, also O epsilon is convex, right? Very, very important. It is convex. Okay. So what is happening is this, for if we start with 2 points y and u in O epsilon, okay, if we do that, that will imply y plus epsilon u, okay, y plus epsilon u will be in O epsilon, where u will be defined is nothing but z minus y, okay. See, what I am trying to do is this O epsilon, so let me draw this part. This is x naught, okay, the ball is at center at x naught, this is O epsilon, Clear? Now you see, this is compact, so you start with any 2 points y and z. You start with any 2 points y and z. Okay, and then the straight line joining y and z. Okay, that should be in O epsilon, because O epsilon is convex. Okay, so the thing is, I am defining a new straight line. So sorry, that line segment containing y and z must be in this. Sorry, line segment, not line. Now you see the straight line which is given by y plus epsilon u, this straight line, this should be also in O epsilon, and what is u here? U is nothing but z minus, I did a small mistake here, u is not in O epsilon, for y in O epsilon. So basically what I am trying to say is this: since y O epsilon is convex, that will imply that y plus epsilon, let's call it u, okay, is in O epsilon, where u is in z minus y, okay, y is z minus y, and 0 less than equal s less than equal 1. Okay, why is this true? See, let's check. You see, y plus epsilon, u is nothing but z minus y, right? So it is nothing but this turns out to be 1 minus epsilon times y plus epsilon z. Okay, so you do realize if epsilon lies between 0 and 1, this will lie in O epsilon. Okay, so if y and z is in O epsilon, then epsilon times z plus 1 minus epsilon times y has to be in O epsilon. So this is what I am writing here in a short thing hand. Okay, yeah, that's fine. Now you see, we define, let phi of x, yes, this is defined as capital F of y plus s u. Okay, see, I am defining a new function. The function is defined from R and is taking values in Rn. Clear? So this is our new definition of psi. Then you see, this inside this function as a function of s is differentiable. Of course, this is a linear function, is differentiable as a function of s. Yes, and capital F is a C1 function, so that is also continuously differentiable. So phi is nothing but the, so since phi is the composition of two C1 function, C1 function. Okay, since it is a composition, what happens is you can talk about the chain rule. Phi prime of s is nothing but the derivative of f, which is df acting at y plus su. Okay, df at y plus su acting at u. Okay, because you know that by chain rule the derivative of this is going to be u, because derivative is with respect to s. Okay, so this is what we are going to get. So therefore what is happening is this. See, therefore what is f of z minus f of y? You remember, for any y and z in that ball, I need to show that f of y minus f of z is dominated by y minus z, the norm. Clear? So I am looking for f of z minus f of y. See, if we do that, this is nothing but psi of 1. What is psi of 1? Psi of 1 is nothing but f of y. Okay, minus psi of 0. What is psi of 0? Psi of 0 is nothing but one second. Sorry, psi of 1 is nothing but f of z, and psi of 0 is nothing but f of y, right? Okay, so this is can be written as 0 to 1, the fundamental theorem of calculus, psi prime of s ds. Okay, and again psi prime of s, we already know what it is. It is 0 to 1 df of y plus su acting at u. Okay, so please understand, df y plus su is nothing but a linear map from Rn to Rn. Okay, Rn to Rn, and this is acting at an element of so this is a map. Okay, and this is acting at an element of Rn. Okay, so this is what it means. Right, now you see what is happening is this, this u, okay, this u is nothing but an element in O epsilon, right? U is the element of O epsilon, okay? And in O epsilon, so if we are just restricting our f to O epsilon, what is happening is this, okay? So let us put it this way. See, if we take the norm of fz minus f of y, okay, that can always be dominated by 0 to 1, the constant times norm of u ds. Okay, why can we do this? See, let's say that I want to show that it is locally Lipschitz, right? So I do not have to look at the whole omega, but in a neighborhood, right? And what is the neighborhood? The neighborhood in our case is O epsilon. Clear? And in O epsilon, since O epsilon is compact, right? We showed that this is true, right? That there is a upper bound, the maximum is attained somewhere. So that maximum I can, if I am taking the norm here, see, if I am taking the norm here, so what do I have? Let me put it this way. Fz minus f of y equals to 0 to 1 df y plus su acting at u ds. This is what we had, right? This is a linear map again, and this is an element of Rn, and this is a linear map from Rn to Rn. Okay, see, if I put a norm in both sides, so there will be a norm on both sides, right? And then this will be dominated by 0 to 1. So this is just a integral, this inequality is coming from the integral inequality. So this is norm of df of y plus su, okay, times norm of u. So this norm is from Rn to Rn norm, and this is Rn norm, right, ds. Now this is always dominated by k, this we saw, okay? So that is what we are going to use here, clear? And you remember how we are getting this thing, so this we already talked about in week 1, so if you do not remember, please go through that. Okay, so this is the case, and now you see, if this is the case, this is nothing but k times the k comes out, it becomes 0 to 1 norm of u ds. And what is u? U is nothing but k times norm of z minus y. Okay, and 0 to 1 ds is 1 essentially. So you see, this holds for all yz in O epsilon. Okay, now the question is this. So this is proved, huh? So this is locally Lipschitz. So basically what I am trying to say is this: if it is continuous differentiability, it is locally Lipschitz. Now think about it this way. Let me ask you this question. Why suddenly locally Lipschitz? Why not Lipschitz? So if f is C1, does that imply f is Lipschitz? We saw it is locally Lipschitz, but is it Lipschitz? Okay, so what about the same this proof? The proof, does it work? Do you think it will work? Of course it won't work, right? Why it won't work? Because you will not get this bound only. The bound which you are going to get here, you see, since it is local, what is happening is this: there is a neighborhood which is going to be compact, and in that compact neighborhood you can have a bound on df. That is very important here, you see, yeah. So without this bound you can't, the whole thing does not really work. Okay, so at least this proof won't work. Okay, but the question is this: is it true that whether it is Lipschitz or not? Okay, the answer is no. I won't say the answer, so you have to do it yourself. Okay, now let's look at the proof of this. What is the proof of what? Proof of our fundamental theorem. Again, let me recall what the fundamental theorem is. We are basically looking at x prime equals to f of x, and x restricted at the point t equals to 0 is x naught. Clear? What I am saying is this: given f is continuous differentiable, just that only continuous differentiability will guarantee a unique solution in some neighborhood of 0. Clear? Okay. So you see, so proof of fundamental theorem. Let us put it this way: of fundamental theorem. This is also called Picard's existence and uniqueness theorem. Okay, so you see, if let's say, okay, let me put it this way, a remark, before we look at the proof, let's do this remark and then we go to the proof. So if x from some I to r, yes, satisfies x prime t equals to f of x of t. If it satisfies this with x0 equals to x0, what does that imply? That will imply that x of t is equals minus x0. So if you are integrating both sides, minus x at the point 0 is nothing but 0 to t f of x of s ds, right? So this is integrating both sides. Clear? Okay, so this form is called the integral form, and you can see that it is actually both ways. Okay, so if you have a C1 function x, then and satisfying the equation, then it will satisfy the integral form. If there is a function which satisfies the integral form, then they are going to satisfy the equation. Clear? So integral form of the differential equation x prime equals to f of x. Clear? Okay, let's look at now we come to the proof of this. So you see, what I am going to do is this. I will show that there is a function which will satisfy the integral form. Once I do that, then you see that if there is a function which satisfies the integral form, then that function has to be the solution of the equation. Okay, so proof. So we will do some assumptions here. First of all, I will write that O rho is a closed ball, okay, closed ball of radius rho positive, and it is centered at x0 and centered at x0. Okay, now what is x0? x0 is the point through which our curve passes at the time t equals to 0. Clear? Okay, A. These are some assumptions. B is there exist a Lipschitz constant. Okay, K for F on O rho. Clear? C, O rho is closed ball. Of course, it's bounded. So what I am trying to do is this: it's compact set, and F you are given to be a C1 function, right, in omega. So when F is restricted to O rho, then we know that this is locally Lipschitz, and hence there is a Lipschitz constant, right? Okay. Now norm of fx, okay, this is always greater than bounded by m on O rho. Again, O rho is compact, right? F is a continuous function, compact set, there is a bound maxima which is, let's call as m, and the thing is we will choose, okay, a, clear, which is less than equal minimum of, so this is just a technical thing, nothing special. I will show you why we need this, but this is just a technical thing which we need. Rho by m 1 by k, okay, and we will write the interval I to be minus a comma a. Okay, so these are our assumptions. With these assumptions, we are going to start by writing down something called a Picard effect. Okay, so what did I tell you? You see, we saw that if there is a C1 map which satisfies this equation, then it has to satisfy this integral form, and vice versa. So essentially we will construct a sequence of function which will actually converge to the integral form, and then that solution will actually be a solution of our equation. That's the idea. Okay, so how do we do something like this? See, we start with some iteration scheme. So we start with the iteration scheme, and this iteration scheme is called Picard iteration. Called Picard iteration. Picard iteration. And what is it? You see, the thing is this Picard iteration. Okay, so the first iterate we are going to define is u naught of t to be x naught of t to be identical equals to x naught. Okay, see, I am trying to somehow approximate the solution. Clear? Now what do we know? The only thing which we know about the solution is at the point t equals to 0. So at time t equals to 0, it has to pass through x naught. So even though it is a very crude approximation, but you can always guarantee that x naught identical equals to x naught. So basically the first function which is identical equals to x naught should always at least is a good approximation, right? Because it passes through the initial point. That's all. Okay, now so define let. Okay, now define the next approximation x1 of t. How do you define the next approximation? You see, I want my approximate functions to do this x at the point t minus x to 0 equals to 0 to t f of x's ds, right? This we want. Okay, we actually want this. You see, you can write this thing as xt equals to what is x0? It is x naught plus 0 to t f of x's ds. Okay, so these are all equivalent. So I want my iterate to converge here. Okay, so I will define it accordingly. I will define it using x naught, which is x naught plus 0 to t f of, you see, x's, right? So I will use the previous x here, which is x naught in our case, x naught of t, s ds. Clear? Okay, so this, if you write it, it is nothing but x naught plus what is x naught of s? It is x naught, right? So it is f of x naught. So t times f of x naught. F of x naught is essentially a constant vector, so I can take it out. So 0 to t ds is t. Now, since t is less than a, right? And you know how we are getting this, right? And the norm of fx naught is less than equal m. Clear? Okay. Therefore, x1 of t minus x naught. Okay. See, what we need to do is this. Essentially, I am starting out at t equals to 0. We are at x naught, right? And the second iterates, or the nth iterate which you are going to get, okay, or the solution which you are going to get must be in the ball O epsilon, right? So basically the x1 of t which you define for all t should be in O epsilon. Okay, how do you guarantee that? So x1 of t minus x naught, I want to make it less than rho. Can I do that? So this is nothing but equals to mod t norm of f x naught, right? This is just basic calculus. So this is dominated by a because mod t is always less than equal a. That is given, right? See, I is between minus a to a. I am taking t from there, so it is always dominated by a. And what is f of x naught? That is given to be m, dominated by a. Where is it given? You see, this is given here. Okay, it is given here. So it is less than am. Now you see, am. Okay, am is less than rho, no? See where you see I chose rho such a way that A is less than minimum of rho and m. So A is always less than rho by m. So AM is always less than rho. Okay. So that is what we are using here. That is what. So as I told you, this condition is a technical condition. Okay. So this is less than rho. Yeah. What does that imply? It implies that x1 of t is always in O rho, this set, okay, for all t I. Okay. See, x naught is a point, is a vector x naught, okay, and O rho is this, okay. O rho is a ball, closed ball, centered at x naught. The iterate which we are finding is such that at all time t, x1 is always in that neighborhood. That's the point. And not only x1, we want all our xn's to be in that neighborhood. Okay. See, now by induction, let's assume by induction, assume that xk of t is defined and the norm of xkt minus x naught is less than rho for all t in I. Clear? So essentially I am saying it is again in O epsilon. So then let define xk plus 1 of t is x naught. So this is our definition of x naught plus 0 to t, the Picardite rate, the k plus 1 Picardite rate, f of x's. I want this to converge to f of x's, right? So I will use the earlier function which is available to us, which is xk in this case, xk of s ds. Clear? So now you see this will make sense. Why? Because see xk of s, okay, so let me put it this way, this makes sense since xk of t is in O epsilon, right? Yes, for all s, yeah. So you see all of this f acting at xk of s, all of this is defined properly, okay, so it's not a problem. Now you see, if you take the norm xk plus 1 of t minus x naught, let's look at this norm. This is always dominated by 0 to root t norm of f of xk of s ds. Clear? Okay. Now you see xk of s is in O rho, yeah, and f restricted to O rho is always bounded by m. So I will just use it like m times 0 to t ds. Clear? Which is m a, okay, which is less than. Why ma? Because it will be empty, right? And t is again dominated by a. T is varying between, you see, t is varying between minus a to a. Okay, so that's bound, that is the bound which I am using here. Okay, so that is fine. Now, so what we have is this. See, by induction we have, therefore you have this sequence x n of t, let's say, okay, which are well defined in O rho. Clear? Now what we will show is, so next we will show, we prove, so we have to prove the convergence, right? So now we will show that this xn, that actually converges to some x of t, which actually happens to be the solution. So next we prove there is a constant L greater than 0 such that for all k greater than equal 0, norm of uk plus 1t minus uk of t is less than equal ak whole power small k times L. Okay, this is what we need to show. So if we show this thing, we basically show it is Cauchy equation, it's a Cauchy sequence, and then all of we can get what we want. Okay, right. So how do we show this? See, so we'll take the maximum of u1 minus u0. Okay, so let L is the maximum of the norm of x1 t minus x0 of t. T lies between minus a to a. Okay, that is possible. Why it is possible? T is varying between minus a to a. x1 and x0 are both continuous function, right? So the maximum exists on a compact set, right? So the maximum exists, and that maximum we'll call it as a. Now you see this L, okay, you can of course see that, and L is less than equal am, right? You see, we proved it, right? Where is it? Yeah, this one, this is norm, right? Okay, so this is your the maxima I am choosing, and I am saying that is L. So L is always bounded by am, which is less than rho, right? So that is always there. Okay, that is what I wrote. L is less than equal am. Now let's look at this norm of x2 of t minus x1 of t. Okay, this is nothing but 0 to t f of x1 of s minus f of x0 of s ds. Okay, the norm. Okay, now you see, I know that this is again dominated by 0 to t k times norm of x1 of s minus x0 of s ds. Okay, this we already know. Why this is true? Because you see, x1 and x0, since x1 of s and x0 of s is in O for all s, right? So that is why we need it in O for all s. So since these are in O for all s, f is Lipschitz continuous in O, right? F is locally Lipschitz, and when f is restricted to O, then f is Lipschitz continuous. So I can take the Lipschitz constant out. Let's just say that constant is k, so that is out, and then we can write it as k times norm of x1 minus x1. Is it okay? Now if this is the case, this is nothing but less than equals to a times k capital L, right? What is capital L? The maximum of x1 and x2. So this can be dominated by L, and then 0 to t ds will be dominated by a. Okay, now I want you guys to do something. This part I am not doing this thing. So you use induction. This you already can do, I think, to show that norm of uk plus 1 of t minus ukt is bounded by ak power k times L. Okay, this I think you guys can show it yourself. Okay, please do this part. Okay, right. Now so this is fine. Yeah, now let alpha equals to ak. So we know that alpha is less than 1. This is our assumption. Yes, see, k we chose it in, see, a is less than equal minimum of this and 1 by k. So ak is always less than 1. Clear? So this ak I am choosing it to be alpha, which is again less than 1. So now you see, given any epsilon positive, we may choose n large enough, okay, so that for any r greater than s greater than n, okay, what do we have? We have x r of t minus x s of t norm is bounded by summation k equals to n to infinity norm of x k plus 1 of t minus x k of t, right? This is again dominated by summation k equals to n to infinity alpha k times L, right? Clear? So this we can do. So this is like the usual calculus stuff. I can just write it like this, okay? And once I can do that, this is always less than equal epsilon. Clear? See, the thing is, why can we do this? Because it is basically a geometric series, right? It is basically a geometric series, okay? And what do you know? We know that since the series converges, the geometric series can be made as small as possible, okay? Now what we do is this. So we show that this is true, huh? So basically what we have is this. We have this equation, the sequence of function, okay? So let me write it this way. You see, we have a sequence of function xn is a sequence of function we have shown that this is Cauchy, so which converges, right? Converges uniformly to a continuous function, x from I to Rn, okay? This is Cauchy sequence, and the convergence is uniform. So basically we know that uniformly convergent sequence, this will actually converge to a continuous function x from I to Rn. Clear? Okay. Also see that xk plus 1 of t is nothing but x naught plus 0 to t capital F of xk of s, xk of s ds. Clear? Okay. Now if you taking limits on both sides, taking limit on both sides, what do we have? We have x of t is nothing but x naught plus limit t tends to infinity 0 to t capital F of xk of s ds. Clear? Yes, I can take the limit inside because of the uniform continuity, and then I have this is x naught plus 0 to t limit t tends to infinity f of xks ds, right? Now see, f is continuous function, it is continuously differentiable, so I can take the limit inside. So I can say this is 0 to t f of xs ds. Clear? So therefore what do we have? Therefore x, we have found a x from I to Odo, okay, which satisfies the integral form of the differential equation, right? Differential equation, okay. So what does it say? It says that it is a solution of the equation, and hence x is in C1. Clear? So we actually got that you have a existence of solution, at least one solution. Yes. Okay, that is there. Now please remember this thing, that the solution which we are getting is in I is minus a. You see, it is in, where is it, I is minus a. Clear? And this minus a is one second, I did some mistake here. Where did I? No, it's okay, a I chose a, fine. Okay, so now you see, so essentially the solution which you are getting is a small neighborhood of 0. Okay, so that is why we are saying this is a local theorem. So basically we are saying that we have a curve which is defined in a small neighborhood of 0 which satisfies the equation and passes through the initial point. Clear? Okay, now the important part is the existence part. So existence part is done. Now the important part is the uniqueness of solution. Now this is not very difficult to prove. Let's do this part, uniqueness of solution. So let's say, let x, y from I to R are two solutions. Sorry, I to x of t is in omega are two solutions of the differential equation x prime equals to f of x satisfying x0 equals to y0 equals to x0. Okay, see why x and y is from I to R. X and y, this basically x of t and y of t, that should also satisfy f of xt, right? And f, the domain is in omega, so basically xt has to be in omega. Clear? So in that sense, essentially. Okay, now you see I have to show that x is equals to y, right? So we have to show x of t equals to y of t for all t in I. So let q is nothing but the maximum, okay, of norm of xt minus yt. And where is t varying between? T is varying between minus a to a. Okay, so this is minus a to a, right? Clear? T is varying between minus a to a. Okay, so that is there. Now this maximum, see, let's say, and okay, let me put it this way. Let's say that this maximum is attained somewhere at the point t1. So t1 is in minus a to a. Okay, so therefore what is happening is this. Okay, first of all, if the maximum can it be attained? Of course it can be attained. See, norm, what did I tell you? Norm is a continuous map, right? How do we show? See, norm from some x to R is a continuous function. Show this first of all. Check this part. Function, check. Okay, right. I already did it. If you remember properly, think of one inequality. Yes, think of one inequality. I already proved it. Yes. Okay. So it is a continuous function while doing Lipschitz continuity. It's a continuous function. Okay, and it's moreover it is Lipschitz continuous actually. And these x and y, these are continuously differentiable. So x minus y is continuously differentiable. Norm x minus y is basically a composition. So it's a continuous map. And on a compact set minus a to a continuous map, there is a maxima. Okay, so now you see q is, I can write it as 0 to t1 x prime of s minus y prime of s ds, right? Why? Because you see this is nothing but mod of xt1 minus yt1. I can write it just like this, right? Clear? Okay. Fine. Now you see this particular thing, I can always do it to be less than equal 0 to t1 f of x of s minus f of y of s ds. Okay, I can do that. Now this is always dominated by, you see, f is dominated by k. F has a bound k, right? So this is always dominated by k times 0 to t1 mod of norm of x of, so this is norm, these are all norm because these are all vectors, these are all norms. So x of s minus y of s ds. Okay, so that is always dominated by a k q. Here now, since see ak is less than 1, then this has to be ak is less than equal ak times q. So since ak is less than 1, the only option is q should be 0. There is no other option. Okay, therefore if k is 0, q is 0, then the maximum of this xt minus yt, the norm of that, is going to be 0. That will imply that xt has to be equals to y of t for all t in minus a. Clear? So the unit test follows. Right. So with this, I am going to end this